All right, continuing on our story with talking about functions and relations and that sort of thing. Let's start with a few bell work problems to see if we remember what we've learned so far. Well, first the question is determine whether the relation is a function, and how do you know? Well, we look and we know that the definition of a function is a set of ordered pairs like this, where each x value is only paired up with one distinct y value. So if I underline all the x values, I notice that the number 1 shows up 2 times in this set of ordered pairs. So then when I look at the y value that showed up with it, I notice it's 2 different numbers. So that's like putting $1 in a vending machine and pushing the same button for whatever candy bar you're trying to get, and you got 2 different candy bars. It's not working in this case. So this would be not a function. Okay, on the second one, we look at this input, it's got 2 different outputs going to do 2 different numbers, as well as so does this one. Each input can only have one arrow leaving it in this type of a chart or configuration. So this would be no, not a function as well. Okay, we've got this equation right here, and we're gonna put it in function form, which means that we're gonna just put it in y equals mx plus b form. So let's take a look at what that looks like. So let's get us a different color, something fresh. Okay, so in order to do this, we need to move x to the other side and put it behind the equal sign. And it becomes minus 2x when it goes over there. So we will be left with minus 2y equals minus 7x subtract 14. And then all we need to do now is divide everything by negative 2 to get y by itself. And our final function or linear equation is y equals 7 over 2 x. And the negatives cancel each other and you get a positive. And then negative 14 divided by negative 2 would be positive 7. So that's what this equation looks like when we write it in function form, or y equals mx plus b form. Okay, now let's look at an inequality word problem. Ryan will run less than 27 miles this week. So we know he's going to run less than 27 miles. So far he has run 12 miles. What are the possible numbers of additional miles he will run? So let's just put m for miles. So far he's already run 12 miles. And he can't go any more than 27 because it might be too hard on his body while he's training for the marathon coming up. So let's minus 12 from both sides. And so the number of miles that he's going to go is somewhere less than 27 minus 12, which is 15. So as long as he runs less than 15 miles, he'll be okay. Okay, so we're going to talk about what we mean by the domain of a function. The domain is all of the x values of the function. So if you think about dots on a coordinate system, all the x values of those dots would be considered the domain. And it's also the input. All right, so let's keep going. So the domain that represents specific countable whole items you can count them up, is called a discrete domain. For example, if I buy a burrito, it costs me 75 cents. So there's an x and y value. If I buy 2 burritos, it's going to cost me $1.50. If I buy 3 burritos, it's going to cost me $2.25. And so on. So each additional burrito adds 75 cents to my total cost. All right. Now, it wouldn't make sense for me to buy 1.01 or 1.2 or 1.5 burritos and then ask how much that costs, okay? Or how many minutes? Let's see. So in that case, it wouldn't make sense to do that. And I'm not sure if this is, I think this is, I'm not sure, maybe this is how long it takes to eat them or something like that instead of how much they cost. In any event, this would be considered a discrete domain. It wouldn't make sense to put dots in between because these are just done in increments of whole burritos. Okay, now a continuous domain, on the other hand, is a domain that represents all values, including decimals. They can be a fraction or a part of, usually something that can be measured, such as height and area. So the height of a wall will determine how much area that wall is going to have on it. And every increase in height, even the decimal amounts between 0 and 1, is going to result in an increase in the amount of area of that wall. So this would be considered a continuous situation, right? Because all the values in between 0 and 1 would also be included in a possible set of solutions. So let's see what this means. So is the domain of the following discrete or continuous? Well, based on this, see how we just put dots on the graph? We're implying then that only the dots are the ones that are important here, not the ones in between the dots. So this would be a domain. Would be discrete, sorry. So the domain is discrete. Okay, how about this one? Well, we've got our line run from 5 on the y-axis to 5 on the x-axis. We've connected all the points in between, so this would be a continuous domain. Okay, take a look at these situations. How about years that have gone by? So like from 1 year to 2 years and so on. And then how much does a cat weigh? Well, normally over time, cats get bigger and bigger each day. And so the fact that it's gone from 5 to 7 to 9 pounds would suggest this is a continuous function because the cat didn't just weigh 5 pounds and then all of a sudden weighed 7 pounds, but it gradually increased in weight over this year until it got to be 7 pounds. So this would be continuous. All right, let's look at this next one. Okay, a belt. If we buy a belt, what's it going to cost in dollars? So no belts, no dollars. One belt ends up costing $7.50, which would imply that 2 belts would cost you double that, which would be $15. So this is considered a discrete domain because you're just buying individual belts that cost an individual amount for each one and not all of the little increments of change in between. Okay, is the domain of the following discrete or continuous? So let's look and see the number of questions on a math test. Well, that would be discrete, right? Because when we do the questions on a math test, we have question 1, question 2, question 3. Okay, the height of a course. So especially if it's growing up, it's just gradually getting bigger and bigger each day. So that would be considered continuous. Okay, the speed of a car on Route 3. So that would also be continuous. And because the car is going at a constant rate of speed, it's always changing as it goes along. And it's just not going to jump from one speed to the next. It's going to be going up or down from one speed to the next and all the ones in between. The number of people in your class, that's going to be discrete. We have a fixed number of individual kids. We don't have 3.24 kids and that type of thing. So it's a discrete number. Fitness club membership has a $100 initiation fee plus 19 monthly fee. So here's the function that represents the amount of money you pay to have to go to the fitness club. So, all right, so that's, I'm not sure what the question is there because it doesn't look like it asked one, huh? There's the function. So that's it. Maybe we better extend the page and see if we're missing some words here. See, on one like this, they're asking us to say if it's continuous or discrete. I better pay attention, huh? You got to read carefully. So the initiation fee is $19 a month. And then, so the function is 19 plus 100 represents the cost Y in dollars of a membership after X months. So this would probably, in my opinion, would be discrete because they are going to charge you an additional fee for each month that you are at the store or at the fitness club. They're not going to charge you by the minute how much you choose the fitness club. So you'd start out with $100, then after a month, $119, then after 2 months, then you would have $138 and so on and so forth. Okay, so here's an equation that represents a function. We could have easily written this as y equals negative 2.5x plus 25, right? Okay, and this represents a prepaid phone card after making a certain number of phone calls. Graph the function using the domain 0, 1, 2, and 3. Is the domain discrete or continuous? So for 0, so we've got to keep in mind that we're going to go up to 25 on here. So we're going to start out with 1. I'm going to number these by 5, 10, 15, 20, 25 up the left side. And then across the bottom, we're going to go 0, 1, 2, 3, 4, 5. This is the domain. So when we put the domain in there, when we put in 0, we end up with 25, right? So let's graph those with a different color. So 0 and 25. If we put in an input an input of 1, that would give us 1 times negative 2.5 and then 25. So if we take off 2.5 of 25, that's going to give us 22.5. So 1 would be at 22.5. So that, and if this is 20, sorry, then 22.5 is going to be about right here. All right, what if we plug in the number 2? 2 times negative 2.5 would be negative 5. Negative 5 plus 25 would be 20. So 2 would be 20. And then the number 3. 3 times negative 2.5 would be negative 7.5, which is, and then, so if you take away 7.5 from 25, you're going to get 20, 19, 18, 17.5. So 17.5 is going to be about right there. And there is the amounts that you would have on your phone card after making a certain number of calls. And so it would not be continuous. It would be discrete because you're being charged by the call, just the amount for that call, not the amount of time you're actually on the phone speaking. So your assignment is going to be the discrete and continuous domain worksheet. It is a pink worksheet, and we'll hand it out to you. Or if you're at home looking at this, you can print it off of our Today page. Thank you very much. All right, so let's keep our discussion going. This is one of my favorite parts of the function unit because we're actually going to be writing some equations today. So let's take a look at what we have here. So the first question is the following a function. Is the x-axis a line that's considered to be a function? Well, let's take a look. Would a vertical line hit the x-axis more than once if I drew a vertical line? No, it wouldn't. So if it will only hit once, not more than once, then it is a function. Okay, over here, if we look at the example here, is the domain discrete or continuous? And in this case, it's phone calls by the number. So each phone call costs a certain amount. And as long as it costs a specific amount, then it would be considered discrete. Now, if you were being measured by continuously monitoring time increments like 1 minute, 1.2 minutes, 1.3 minutes, and so on and so forth, then that would be considered continuous. And that was what kind of looks a little similar like that here, but this only says cell phones 1, 2, and 3. So in fact, in this case, it might be how many phones you have on your plan instead of the number of phone calls you make. So one plan, $45, 2 phones on your plan, they bump it up a little bit, but it's still a discrete amount. Okay, number 3, the number of shirts and shorts that you can buy with $30 is represented in the following explanation. This particular table of values. So if you get 0 shirts and 6 shorts, it'll cost you $30. If you get 1 pair of shorts and 4 shirts, $30, and so on and so forth. And 3 shirts and no shorts cost you $30. So write the equation in function form for that setup right there. So what we're going to do is so here's the equation that we've got. So we're going to have to solve it for y. So 10x plus 5y equals 30. So to write it in function form, we just solve for y. So we put 5y in front where it wants to be, then the equal sign. The 10x gets moved to behind the equal sign, and because it crosses the equal sign, it becomes its opposite. And the plus 30 is still there. We just put a plus in front of it so we don't lose track that it's positive. Then we divide everything by 5. And then when we do that, we end up with y equals, and negative 10 divided by 5 is actually negative 2x, and 30 divided by 5 is a positive 6. So there's y equals mx plus b, or the other name about that it takes on is a function or function form. Okay, so we answered this question right here. Now, why is x equal 4 not in the domain? So if you look at this particular function right here, I want to make sure I'm not looking at something different. Why would 4 not be in the domain of this particular function? Well, if we graph it, let's take a look. Y equals negative 2x plus 6, so we would start at 6 and go down 2 over 2, down 2 over 2, down 2 over 2. So this is what it would look like if we graphed that function. Okay, so y equals 4, or x equals 4, not in the function. Well, if you look at it, here's x equals 4. So it doesn't even intersect the graph. So that's why it's not in the domain, because it doesn't even intersect the graph. And this would not keep going down below the x-axis because the cost of shorts and shirts are never going to be negative. Okay, is the domain discrete or continuous in this particular situation? Well, because we're talking about individual pairs of shorts or individual shirts, and for individual amounts of money, this would be considered discrete. And there we go. Okay, so let's go on to the next one. Okay, now what we're going to do now is we're going to write a linear function for the line that we have on the graph. And basically all this means is we are going to write an equation in slope-intercept form. And this is something that we've already done before, at least when we're looking at a line. So first of all, we got to find m, tell us what that equals, and that's the slope. Then we got to find b, and then we're going to write the equation, right? So m, in order to write m, we've got to find a couple of good intersections. There's one, that's a y-intercept. And then here's another one where it crosses right at an intersection there. All of these others would be estimates as far as where it crosses. So now let's look at our rise and our run. So to go up 1, 2, 3. So that's the number we put on top, 3. I'm having a little hard time writing here. Sorry, let's try that again. Let's get that 3 written again. So 3 on top of our slope. And then from there we go over 1, 2, 3, 4, 5. So there's our slope, 3/5. Then we look at our y-intercept. Where did it cross initially? It crossed the y-axis at -1. So then let's write the entire equation. It's just y equals 3/5 x subtract 1. So we wrote a linear function or a linear equation that matched this graph. And we've done this before. We're just calling it something different today because these equations take on several meanings. All right, so here's one. Write a linear function that relates x to y. So we notice we've got a line that comes down through here. We notice that the y-intercept, or b, equals 1. And then to go from one dot to the next, we go down 2 over 1. So our slope would be down 2 over 1. And now we're going to write the function in slope-intercept form. Y equals -2 over 1x plus the y-intercept. So there's the equation for that function. And to be honest with you, you really don't need to put the 1 on the bottom, but I'm putting it there just because I don't want you to lose track of how we got that. Okay, for our next one, this one's a table of values, so we've got to come up with our slope, which is the change in y. So our change in y to go from -2 to -1 is an increase of 1. To go from -1 to 0, that's a bump up of 1, bump up of 1. So it looks like for our slope, the change in y is 1. What's the change in x? To go from -10 to -5 and from -5 to 0 and from 0 to 5, they're jumping up by amounts of 5. So our slope is up 1 over 5. Now don't get confused because they've put the y on the bottom and the x on the top. Don't let that confuse you. When you write the slope, the change in y goes on the top. Now b, what is the y-intercept? Well, at the y-intercept, that's when the x value is 0. So if I find where x is 0 and then look down, what's my y-intercept? In this case, it happens to be 0. Oh, that makes it real easy to write this equation. So our equation is just going to be y equals 1/5 x And that's all I have to write. If I did write plus 0, that would be okay, just so you would know that the y-intercept goes through 0, 0 instead of like 1 or some other point. All right, let's keep it going. Write a linear function that relates y to x. Okay, so in this case, our change in y to go from 2 to 4, from 4 to 6, from 6 to 8, looks like we're bumping up by 2, right? Bumping up by 2. Okay, how about the x's? -6 to 2, -2 to 2, and 2 to 6. If I'm not mistaken, we're jumping up by 4 each time here. Good thing you know how to count in this way. So our change in y over our change in x is 2 over 4, which simplifies to be 1/2. And that's m. So our m in this case is 1/2. Okay, well, what's b then? What is our y-intercept? Well, we said that the y-intercept is when x equals 0. Well, we don't have an x equals 0 here, but we do have a way to find it. So we notice that 0 is going to be halfway in between -2 and 2 right here. So 0 on this, if we were able to find it on this chart, is halfway in between -2 and 2, which means that the y value is going to be halfway in between 4 and 5. So, or 4 and 6, which would make our y-intercept 5, right? So in this case, we actually had to kind of look at the table of values and do a little bit of interpolating, if you will, or estimating, and trying to see where it would be if we were able to get those numbers plugged into the function. So our linear equation or linear function would then be y equals 1/2 x plus 5. So again, we had to estimate b by just trying to figure out where 0 would be on this set of ordered pairs. If we were bumping up along here, instead of going up 4, we only went up 2 from -2, which would put us at 0. And then that also put us at 5 on the y column. All right. So let's try. We got how many more? We got a couple more to go. So let's keep it up. So on this one, b equals -1, and our slope is up 2 over 2. So up 2 over 2, which simplifies to be just 1. So our equation will be y equals 1x minus 1. That's our linear function. That's a pretty easy one, isn't it? Okay, our next one. So we've got b, the y-intercept, is -3. And then our slope m is up 1 over 2. Up 1 over 2. Okay, now we better take a little closer look at that. Is it really up 1 over 2? This is up 1, but in the x direction, that is actually over 3. Look at that. They've got this numbered differently here. So our bottom number is not going to be 2. It's going to be up 1 and over 3. So when you're doing these, take a look at your scale here and make sure you're writing them according to the scale that's written there. So y equals 1/3 x minus 3. And if you had to, you could, if you didn't have any coordinate system with dots on it already, you could graph that quite easily because we know how to graph a linear equation. Okay, so here's a word problem that we need to take a look at. The table shows the cost y in dollars of x ounces of brewed coffee. So 8 ounces cost 50 cents. 16 ounces cost $1. 24 ounces cost $1.50. So which variable is independent? Well, we know that the independent variable is X, the number of ounces that you buy. You get to choose that. So graph the data. Okay, is the domain discrete or continuous? So if we put that on a graph, we would notice that you could buy incrementally smaller amounts than just a half ounce or 1 ounce, unless the company is only going to give you 8 ounces or 16 ounces or 24 ounces. So it kind of depends on how you look at it. But if we just base it off of this graph right here, or this table of values, we would say the domain is discrete. Okay, and then write a linear function that relates y to x. So we notice that when x is 0, what's the y value? 0. So that means our y-intercept, if we were to graph this, is 0. And then what's our slope? For every 8 ounces we go up by 50 cents, right? So m would be 8 over 0.50, 8 ounces for 50 cents. Now, if we wanted to, we could make this something over 1. So if we double the 50 cents and we wanted to get this m over 1 with something over 1 to make it a little more simple, then if we double 50 cents to get 1, we'd have to double 8 to get 16, right? Oh, and there it is right there. Look at that. So that's our slope. M equals 16 over 1, right? So for every ounce I go up 16, or every 16 ounces I go up $1 in cost. So the coffee is really costing me $1 for every 16 ounces. Okay, how much does it cost to purchase 32 ounces of brewed coffee? Well, since I found out that it's costing me 16, each 16 ounces is costing me $1, then 32 ounces is double what 16 is, so that would equal $2. And if we had this on a graph, which I don't have a lot of room to make on here, we would be able to look at it on a graph as well. Okay? And it says to graph the data, but we don't have room to graph it in this case. All right, so our next one, the formula for the area of a triangle A is equal to 1/2 B times the height. 1/2 the base times the height. What is the height in feet of the base of the triangle? So D, what's the height? What is the length in feet of the base of the triangle? So 1/2 the base times the height. What is the length of the base? Okay, so let's take a look. If we plug in one of these numbers, the area of 9, let's put that in there. We'll just use these numbers. And that equals 1/2 the base times 3. That's B for base, sorry about that. Okay, so that's what the area is. So actually, let's write that again. We need to get that more accurately written. The area is 9, right? So 9 equals 1/2 the base times the height, which in this case is 3. So if I multiply 3 times 1/2, I get 9 equals 3/2 times the base. Or if I divide by 3 over 2 to get base by itself, So then I would flip and multiply. I would get 18 over 3. So the base in this case would equal 6 because it would be 2/3 of 9. So interesting. So what it would be the length in feet of the base of the triangle? It would be 6. All right, that's kind of interesting, isn't it? So good luck with our worksheet. I got several examples that we've just shown you. You can go back and check out the video on Canvas if you'd like to, or ask questions as we go along. Thank you very much.